Um, usually when we think about graphing something out in math, there's this comforting expectation of a simple, orderly progression.
Right, yeah. Like a direct relationship.
Exactly. You move a little to the right along the bottom, and you move a little up or down on the vertical axis. It's just a world of pure cause and effect.
Yeah.
Moving right dictates what happens next.
Well, it's a very structured way to view reality for sure. The math textbooks call it a direct, explicit, functional relationship.
Right.
As long as you keep moving forward, the equation behaves perfectly.
But then, you step out of the textbook and you look at almost anything moving in the actual physical world, and suddenly that clean left to right progression just shatters.
Oh, entirely. Yeah.
Like imagine tracking a fly buzzing erratically around a room, or a roller coaster doing a massive overlapping loop-the-loop. The path constantly crosses over itself. It loops backward.
Which is a huge problem for standard equations.
Right. And if you try to force that looping movement into a standard algebra equation, the math literally hits a wall. The entire system breaks because you can't have two different heights at the exact same forward position without violating like the most basic rules of standard functions.
Yeah, that is the absolute definition of a mathematical breakdown. The standard tools you spent years learning are suddenly, well, completely useless.
Wow.
You're trying to use a two-dimensional grid to explain a dynamic event, and the grid simply can't handle the complexity of paths that retrace their own steps.
And that mathematical breakdown is exactly what we are exploring today in our deep dive into your notes. Specifically, the material from your Day 15 stack on parametric differentiation in engineering domains.
It's a fascinating stack.
It really is. So our mission today is to unpack exactly what happens when traditional math hits that wall in the real world, and how introducing a single hidden variable kind of rescues the whole system.
But rescues it and redefines it, really.
Yeah, we're going to look at how this mathematical shift takes us all the way from tracking an abstract circle to ensuring spacecraft don't tear apart in orbit, or preventing invisible power grids from melting down, and even keeping heavy industrial robots from literally breaking their own arms.
The paradigm shift here is profound. I mean, we have to completely abandon that simple cause and effect relationship where a vertical position simply depends on a horizontal one.
Right, we have to throw that out.
Exactly. Instead, we have to look at situations where both of those spatial directions are being driven independently by something else entirely, like an underlying engine.
Okay.
And most of the time, in the real physical world, that hidden engine is time.
I always like to picture a sketch for this. Like if you ever played with one, you don't just magically draw a perfectly smooth diagonal line by just, wishing the cursor to move diagonally.
Right. You have the two knobs.
Exactly. You have a horizontal knob, and you have a vertical knob. The vertical movement doesn't depend on what the horizontal knob is doing. Both knobs are being turned independently by your two hands.
Yes.
And your hands are turning them over a shared period of time. So time is the hidden parameter pulling the strings.
That is a brilliant physical representation of what parametric equations actually are. Your hands act as that parameter, let's call it for time, driving the horizontal and vertical outputs simultaneously.
Okay, makes sense.
Now, mathematically, the challenge is figuring out the overall rate of change. Like, how do we find the steepness of the line on the etch-sketch at any given microsecond?
We use the chain rule.
Right.
Spot on.
Yeah.
We calculate the rate of change of the vertical position over time and compare it to the rate of change of the horizontal position over time.
So we essentially take the vertical speed, which is driven by my left hand, and divide it by the horizontal speed, driven by my right hand.
Exactly.
And as long as my right hand doesn't completely stop moving, which would give us a dreaded division by zero, we get our first derivative.
Right.
We know our instantaneous speed and direction on the screen. I mean, it seems fairly straightforward.
Well, the first derivative is straightforward. It's elegant. But this is exactly where the danger lies.
Uh-oh.
Yeah. Everything feels so logical and simple that engineers and students get lulled into a false sense of security. The trouble begins when you need to calculate the second derivative, the acceleration.
Yeah, your notes heavily flag this as a critical trap, like a fatal error that fundamentally breaks the underlying physics of whatever you're trying to build.
It really does.
I have to admit, looking at the notation for this, the trap seems incredibly easy to fall into. If I found the first derivative by just dividing the vertical rate by the horizontal rate, my instinct is absolutely to just do the exact same thing again.
Just stack them. Right?
Yeah, just take the second derivative of the vertical, divide it by the second derivative of the horizontal, and call it a day. It looks like a simple fraction on the page, so our brains just treat it like one.
And that's the trap. The notation creates a powerful optical illusion. It implies a symmetry that simply does not exist at the second-order level.
Why not?
Well, if you step back and look at the physical reality, a second derivative is measuring how fast your first derivative is changing. But your first derivative is now, fundamentally speaking, the language of time.
Oh, I see.
It's a time-based function. You can't just casually measure a time-based function using a spatial ruler without paying a tool.
Wow, I love that framing.
Yeah.
So we're fundamentally operating in different dimensions now.
Exactly.
We're trying to measure how the steepness of the line changes as we move across the screen, but our stopwatch is running independently of the screen. We need a translator between time and space.
And that translator is what your notes call the nonlinear scaling step-down factor.
Nonlinear scaling step-down factor.
Right. When you take the derivative of your first derivative with respect to time, you aren't done. You absolutely must scale that result by multiplying it by how time relates to horizontal space.
Wait, or to think of it another way, you have to divide your new time-based calculation by the horizontal velocity.
Yes, exactly. Because if you ignore that step-down scaling factor, you're essentially pretending that the horizontal knob on your Etch-a-Sketch is turning at a perfectly constant speed of 1 tick per second forever.
Which it isn't. I mean, you might be turning that knob frantically or barely moving it at all.
Right. By ignoring the scaling factor, your math becomes entirely unmoored from physical reality. You're calculating the acceleration of a car, but completely failing to account for the fact that the clock on the dashboard is ticking at a wildly variable speed.
Oh, wow.
The scaling factor forces the calculation back to the real world.
That makes so much sense. I mean, abstract math and avoiding fatal calculation errors is definitely a plus, but I really want to see how this geometry actually behaves when we track physical motion.
Sure.
If we move past the Etch-a-Sketch, how does this look in open space? This brings up the analytical case in your notes, which is tracking a point moving in a perfect circle.
A circle is the ultimate test case because it inherently violates standard math. It loops entirely back on itself.
Right.
So we separate it out. We map the horizontal movement to a wave function, a cosine wave, and the vertical movement to a sine wave. As time ticks forward, these two waves oscillate out of sync, perfectly charting a circular path.
Okay.
We now have a position vector tracking exactly where we are on the edge of the circle at any given second.
Let's trace the behavior of the math here without getting, too bogged down in the actual formulas. If we want to know the velocity, we take the first derivative of those waves.
Exactly. The waves shift. The rate of change of a cosine wave acts like a negative sine wave, and the rate of change of a sine wave acts like a cosine wave.
Okay.
Together, these shifted waves give us our velocity vector. It tells us the instantaneous speed and the exact tangential direction the point is flying along the edge of the circle.
But the real revelation happens when we calculate the acceleration, right? When we take that second-order time derivative, we differentiate our shifted velocity waves one more time.
Yes. When you take the derivative of those waves a second time, the sines and cosines swap again, and they flip their positive and negative signs. The math elegantly folds completely back in on itself.
I remember reading this in the notes and being completely blown away.
It's incredible.
The original position vector points outward, from the center of the circle to the edge. But when the math folds in on itself for the second derivative, it proves that the spatial acceleration vector is the exact negative inverse of the position vector.
Yes.
It points from the edge directly backwards straight into the dead center of the circle.
It's a mathematical proof of a physical reality. I mean, we didn't introduce gravity or physical tethers into the equation. The pure, unadulterated geometry dictates that if an object is moving in a circle, there is a constant, unavoidable acceleration vector pointing inward.
It's the mathematical origin of centripetal acceleration. Like if you've ever swung a heavy bucket on the end of a rope, you feel the rope pulling tight.
Absolutely.
The math proves exactly why that rope feels tight. The acceleration isn't pushing the bucket forward, it's constantly pulling it inward to maintain the circular path.
And this specific relationship, understanding precisely how that inward-pointing second derivative behaves over time, is the fundamental blueprint for keeping monumental engineering projects from violently falling apart.
Well, we can clearly visualize that inward pull on a chalkboard circle or swinging a bucket, but let's scale that up into the actual engineering domains from the notes.
Let's do it.
Because a satellite in orbit is basically a very expensive bucket on an invisible rope of gravity. How do aerospace engineers actually use this scaling math to keep things from breaking?
We have to remember that orbits are almost never perfect circles. Satellites move in complex elliptical paths around the Earth.
Right, right.
The distance from the planet changes constantly, which means the speed of the satellite and the strength of the inward gravitational pull are fluctuating at every millisecond of the journey.
They're whipping around the planet, moving incredibly fast when they sweep in close and slowing down as they swing further out.
Precisely. So structural engineers use the first parametric derivative to map the ever-changing instantaneous orbital velocity. But velocity doesn't snap metal. Acceleration snaps metal.
Oof, yeah.
To understand the physical stress on the spacecraft frame, they need the second parametric derivative. It reveals the precise gravitational load, the dynamic g-forces acting on every joint and rivet of the spacecraft at any specific point along that ellipse.
And here's where the fatal math trap we talked about earlier becomes literally fatal. If an engineer gets lazy and just divides the 2-second derivatives without using that time-translating step-down factor, their math assumes the satellite is moving at a uniform rate.
Which is a huge mistake.
Right.
Yeah.
They might vastly underestimate the inward g-force during the fastest, closest part of the orbit.
The calculated stress limits would be entirely wrong. The structural frame wouldn't be reinforced adequately, and as the satellite hit peak acceleration, the sheer mechanical stress of the momentum fighting the gravitational pull could literally tear the metal apart in a vacuum.
Wow.
The math literally dictates the required thickness of the titanium.
It's incredible to think that a missed denominator in a calculus equation is the difference between a functional communication satellite and a cloud of very expensive orbital shrapnel.
It really is.
But we can visually imagine a satellite breaking apart. What happens when this exact same mathematical chaos happens in systems we can't even see with the naked eye? Like if we zoom down into a city's electrical grid, how does this parametric logic apply to alternating current?
Alternating current, or AC power, is incredibly difficult to conceptualize because it isn't a steady stream of energy flowing through a pipe.
Okay.
AC voltage and current are cyclical phenomena. They pulse, they oscillate back and forth. To understand them, electrical engineers model these invisible waves as vectors rotating over time, which are known as phasors.
Rotating over time. So we're back to circles, and we're back to our hidden parameter, time driving the entire system.
Exactly. In a complex electrical grid, you have a voltage wave and you have a current wave. In a perfect world, they pulse perfectly in unison. But real grids are messy.
How so?
Well, they're full of capacitive and inductive elements like massive coils and transformers that inherently resist changes in the flow of electricity. This resistance causes the current wave to lag behind the voltage wave.
Got it.
They fall out of perfect synchronization, creating what is called a phase shift.
So how do engineers visualize a lagging invisible wave against a leading one?
They plot them parametrically. They use the hidden parameter of time to map the current wave on one axis against the voltage wave on the other. Instead of a clean circle, this creates a highly complex, geometrically looping figure known as a Lissajous pattern.
Oh. If you've ever seen an old-school oscilloscope screen in a sci-fi movie with those glowing green overlapping pretzel shapes, that's a Lissajous pattern.
That's exactly what it is.
It's a visual manifestation of two competing frequencies, plotting a looping path.
And they're mesmerizing to look at, but they contain vital diagnostic data. By calculating the second-order parametric derivative of that looping pattern, engineers can map out the dynamic stability constraints of the entire electrical grid.
Wow.
They can predict how those lagging inductive elements will behave under sudden stress.
Let's ground that dynamic stability concept for a second.
Yeah.
What is the physical mechanism here? And what are the actual stakes for the grid if an electrical engineer miscalculates that second derivative?
Well, the stakes are the survival of the power grid itself.
Jeez.
Inductive coils store energy magnetically. When the current and voltage fall out of sync, the energy isn't flowing smoothly. If the math predicting how those waves accelerate relative to one another is wrong, the system can experience grid resonance.
Meaning the waves start compounding on top of each other instead of balancing out.
Exactly. The electrical oscillations hit a feedback loop. Instead of the coil damping a surge, it violently releases stored energy at the exact wrong microsecond, amplifying the waves.
Oh, no.
Yeah, the voltage spikes massively, creating a surge that physically overheats and melts the copper inside the transformers. Misinterpreting the second derivative of a Lissajous pattern can ultimately cause catastrophic, localized power failures.
That's terrifying.
Entire neighborhoods go dark because the dynamic stability of a shifting, invisible wave wasn't properly scaled.
It is wild that the same mathematical principle that keeps a satellite in orbit keeps our refrigerators running.
It's universal.
But we've been talking about tracking natural forces,
Yeah.
gravity's pull or the cyclical nature of electrons.
Yeah.
What happens when human beings decide to play creator?
Ah, right.
When we aren't just tracking a natural path, but artificially designing our own complex movements in something like robotics?
When we try to engineer artificial movement, we run headfirst into the exact same problem. Whether you're programming the control loop for an industrial robot or building a 3D computer graphics engine for a movie, you rarely want an object to move in a rigid straight line.
Right, that would look awful.
You need fluid, smooth paths that can snake around obstacles. But fluid paths inevitably loop back on themselves.
Which means we are back to violating the vertical line test of basic algebra. You can't program a robotic arm to reach inside a car chassis, weld a seam, and pull back out using standard functions. The math fundamentally cannot process the overlapping path.
Standard functions are entirely blind to the overlapping complexity. So programmers and engineers rely on parametric Bezier curves, or B-splines.
Okay.
They abandon the spatial grid entirely and map every single desired coordinate along the robot's intended path strictly to the hidden parameter of time.
So we map the journey out millisecond by millisecond. And just like with the satellite, taking the first derivative sets the velocity orientation. It tells the robot's onboard computer the exact heading and speed the arm needs to travel at any given moment. But for a robot to function without destroying itself, the critical piece is the second derivative, right?
Yes.
The second derivative verifies what engineers call C-squared continuity.
C-squared continuity is the holy grail of physical motion control. It stands for curvature continuity.
Okay.
It isn't enough for two different sections of a path to simply meet at the same point, and it isn't enough for the robot to be moving at the same speed when it transitions between those sections. Curvature continuity demands that the rate of change of the underlying acceleration matches flawlessly across the transition point.
I always try to translate this by thinking about driving a car at highway speeds.
Good analogy.
Like if you are driving perfectly straight and you somehow instantaneously jerk the steering wheel a full 90 degrees to the right, your path on a map is technically connected.
Right.
But your curvature continuity is utterly non-existent. You have just subjected your car and your body to infinite jerk.
Infinite jerk is the perfect term for it. In the digital realm, if a video game engine lacks C-squared continuity in its camera swoops, the transition is abrupt. The physics engine glitches, resulting in sudden visual tearing on your screen that can literally make you feel nauseous because your brain recognizes the acceleration is physically impossible.
But when we move out of the digital realm or into the physical world of heavy robotics, the stakes are so much higher than a glitchy screen. Imagine a massive, multi-ton industrial robot arm swinging around on an assembly line.
Yes.
It's moving heavy metal components incredibly fast.
If the programmer failed to use parametric math to ensure C-squared continuity, if that multi-ton robotic joint is suddenly told to abruptly change its acceleration vector without a mathematically smooth transition, the sheer physical momentum of that heavy metal arm is still carrying it violently in the old direction, while the motors desperately try to achieve infinite acceleration in the new direction.
The motors are literally fighting the mass of the arm itself.
Exactly.
The machine will shear its own bolts off. It could snap its own arm in half, simply because it was fed math that lacked a proper secondary derivative scaling factor.
The math is the invisible safety rail. A properly scaled second-order parametric equation guarantees that the mechanical actuators transition smoothly, absorbing the momentum gracefully and keeping physical machines intact under extreme operational stress.
Taking a step back and looking at the whole picture, it is just an incredible journey through these notes. We started with what seemed like a hyper-pedantic warning,
Yeah, just a math rule.
A reminder not to take a lazy shortcut when dividing fractions, and to remember to scale a second derivative back into reality using a time translation factor. But we've seen how that single mathematical truth is the linchpin for everything.
It really is.
It's the math that translates to surviving crushing G-forces on a spaceship, damping resonance to avoid rolling blackouts in our power grids, and calculating curvature continuity to keep industrial robots from tearing themselves apart.
The deepest takeaway here is realizing that the most abstract, seemingly theoretical rules of calculus are the very physical threads holding our modern infrastructure together.
Absolutely.
And I think it's crucial to highlight a fascinating computational proof note included at the very bottom of your source material.
Oh, right. The section on the coding validation.
Exactly. Your notes detail using Python libraries, specifically SymPy for the symbolic math, to let a computer flawlessly process the complex derivative scaling equations without the risk of human error.
Right. Taking the human error out of it.
Yeah, and then feeding that pure math into NumPy and Matplotlib to construct geometric validation plots. It showcases the reality of modern engineering. We don't just blindly trust a human scribbling equations on a whiteboard anymore.
Thank goodness for that.
Seriously, humans and computers work dynamically hand in hand to process these invisible forces, calculating the extreme vectors and visually plotting the litigious patterns or the robot's physical path to absolutely guarantee they will behave predictably in the real world.
It takes the invisible math and renders it visible. It proves that our complicated mathematical etch, a sketch, is actually drawing the safe, continuous path we think it's drawing.
It visualizes the hidden parameter.
Which brings us to the end of our deep dive today. But before we sign off, there is a fascinating, almost philosophical thought experiment embedded in this concept that we want to leave you with.
It's a good one.
We've spent the entire time looking at how tracking this hidden parameter of time allows us to finally predict and control the behavior of incredibly complex systems. Systems that, without the parameter, just look like a tangled, overlapping, chaotic mess that breaks all the standard rules of logic.
It forces you to look at the world differently. I mean, if our actual physical reality, from the immense gravity pulling on orbital satellites to the microscopic chaotic dance of alternating electrical currents to the physical swing of a massive mechanical arm, is truly dictated and stabilized by these underlying hidden parameters.
What other wildly complex situations in life or in nature seem totally chaotic, broken, and unpredictable on the surface, but might actually make perfect, elegant sense if we could just discover the hidden parameter that's secretly driving them?
Exactly.
Think about that the next time you see something in life looping endlessly back on itself.
The parametric logic suggests that the chaos is just an illusion. There is always a hidden driver if you just know how to adjust your perspective to look for it.
Keep looking. We'll catch you on the next deep dive.